So in this video, I'm going to show you how to compute certain trigonometric integrals that you could not do back in Calc 2. And so we're going to use complex analysis to solve some of these integrals. Okay, so basically we have, in general, an integral of this form where our function f is a rational function of cosine and sine. Okay, so what we're going to do is we're basically going to take an integral of this form that's a real integral, and we're going to convert it to a contour integral over a closed curve C that is actually the unit circle. Okay, so that's the first step, and then the second step is we're going to use Cauchy's residue theorem. And so if you recall, Cauchy's residue theorem basically takes a contour integral, and you can compute that contour integral by finding residues and then taking a finite sum of those residues times 2 pi I. Okay. All right, so for part 1, the conversion to the contour integral, we do the following. We let z equal e to the I theta, right? And then we find dz, which is I e to the I theta d theta. And then rearranging some things, we have d theta is dz over iz. In addition, we also have cosine of theta equal to 1/2 of z plus 1 over z, and sine of theta equal to 1 over 2i times z minus 1 over z. Okay, so here we have d theta in terms of z and dz, cosine theta in terms of z, and sine theta in terms of z. And so what we're going to do is we're going to plug these things into our trig integral to get our contour integral. Okay, so let's take a look at an example. So the example we're going to do is we are going to integrate from 0 to 2 pi 1 over 2 plus cosine theta d theta. Okay, so if you think back to your Calc 2 days, there's no technique that you learned back in Calc 2 that would allow you to do this integral. Okay, so based on what we had written on the board, this is going to equal an integral over C. It's the unit circle. 1 over 2 plus, so cosine theta was 1/2 z plus 1 over z, and d theta was dz over I c. Okay, and so I can factor out this I that's in the denominator, and then I can distribute the z as well, and ultimately this leads to, so I can factor out the I from the denominator, and then I can multiply top and bottom by minus I, and so that leads to minus I integral over C, 1 over, so let's see here, we'll have a 1/2 z squared, and then plus 2z, and then plus a 1/2. Okay, and then if I multiply the top and bottom by 2, I'll get rid of the fractions in the denominator. This is equal to minus I integral over C of 2 divided by z squared plus 4z plus 1 dz. And I mean, I could factor out the 2 as well, but I'll leave the 2 there. So now we've converted our real trigonometric integral to this complex contour integral. All right, and so now to use the Cauchy's residue theorem, we have to, well, find roots of this quadratic. So you'll note that the roots of this quadratic are, the roots of z squared plus 4c plus 1 are, I'm going to label them, I'm going to call them alpha 1 and alpha 2. So alpha 1 is root 3 minus 2, and alpha 2 is minus root 3 minus 2. And so, with these as the roots, we have to determine if any of these roots actually are inside the unit circle. And so you'll notice that alpha 1 has magnitude less than 1, and so it's inside the unit circle. But alpha 2 has magnitude greater than 1, so it's outside of the unit circle. Okay. So we need to find the residue of alpha 1 for the integrander. Okay. So we're going to find the residue of 2 divided by, and I'm going to actually factor the denominator. Okay. So this is our function that we want to find the residue of. So we want to find that residue at alpha 1. This is what we want to find. So this is actually equal to, by theorem 1 in chapter 6, it's equal to the limit. Okay, so we also have to think about the fact that alpha 1 is a pole, but it's a simple pole. And so since it's a simple pole, we take the limit as z goes to alpha 1. We don't have to do any derivative here. It's simply the limit of z minus alpha 1 times our function 2 over z minus alpha 1 times z minus alpha 2. Okay. So of course these guys cancel, and it's simply a matter of plugging in alpha 1 into this expression here, and so it turns out to be 2 divided by, so a difference between alpha 1 and alpha 2. So let's see, turns out to be 2 root 3 in the denominator. So of course these 2's cancel, we get 1 over root 3. All right? And by Cauchy's residue theorem, this integral equals, well, this integral here equals 2 pi I times 1 over root 3. Okay, so this leads to that the integral from 0 to 2 pi 1 over 2 plus cosine theta d theta is equal to, first I account for the minus I that's in front of our contour interval, times 2 pi I, and then times 1 over root 3, which was that computation of the residue. And so this turns out to equal 2 pi over square root of 3.